So now we look at some applications for the first law of thermodynamics. Now I talked about how the first law means that the internal energy of a system can be used to create work, for that system to do work. But another way of looking at it is, if you remember the equation that we had, right, delta U, the change in internal energy was equal to Q minus W. Well, if delta U is 0, if there's no change in internal energy, then Q is equal to W, right, for delta U equals 0. So the heat, or the net heat, into the system is equal to the work done by that system. So if we add heat to a system, we can actually do work. That device is called a heat engine. A heat engine is any device that converts heat into work. Your car's engine is a heat engine. Steam engine is a heat engine. A nuclear power plant is a heat engine. So we have some system here, shown here by the dotted black line. Heat is going into the system through some process. Now, where that heat comes from varies. In your car, it's by burning gasoline. When you burn gasoline, that's a chemical process that releases heat. In a nuclear power plant, it's the radioactive decay of the uranium or plutonium or whatever they're using to power that nuclear power plant that is creating the heat. For steam engines, it's basically boiling the water from burning wood or coal. So heat is going into the system. That system does work, and heat leaves the system. So we'll learn later, with what's called the second law of thermodynamics, that all the heat you put into a system cannot be spat out as work. That you'll always have waste heat coming out of this process. So the work coming out of this system plus the heat coming out of this system has to equal the heat going into the system. So if you know how much heat is going into a system, and you can figure out, again, we'll use the second law of thermodynamics to figure this out later on in this lecture series. Work that is emitted, right, the work that's done by the system. If all the heat went into work, it would be a 100% efficient engine. But sadly, no such engine exists. All engines produce some waste heat. For your automobile, that's easy, very easy to see, right? You're burning fuel inside the cylinders of your car. That causes the hot gas to expand, causing your car to do work, right? Move your car forward. But there's waste heat, right? Your exhaust. Your exhaust, the gases coming out of the back of your car are hot. Hotter than the ambient air. Not as hot as they originally were in the cylinder when the gasoline was first fired, but still very hot. If you have a motorcycle, you might have burned yourself on the exhaust pipe at some point in time. That's the waste heat that's coming out of that system. So when we're talking about a heat engine, we're talking about ideal gas laws, right? Some process is going on. PV is equal to nRT, or PV is equal to capital N, in case of BT, right? Both versions of the ideal gas law. The first one is used more by chemists, the second one is used more by physicists, but they're identical in concept. So we have to look more closely at this ideal gas law. And to do that, we're going to go back to the concept of PV diagrams. PV diagrams are just diagrams where the pressure is plotted against the volume. So change in pressure versus change in volume. The work done on or by a system like the one here, going from one state to another. And by state, I mean a given set of values for the ideal gas law. So a very pressure, volume, and temperature in one state. Another state might have a different pressure, volume, and temperature. Or just a different pressure and volume. Or maybe just a different pressure. But if two engines have the same pressure, the same volume, and the same temperature, if two heat engines have the same pressure, volume, and temperature, we say they're in the same state. If you change any one or all three of those variables, we say the state has changed. So the work done on or by a system going from one state to another equals the area under the curve of a PV diagram. So we're going to show you a couple of simple examples. Now, the area under the curve is technically calculus, right? But we're going to look at simple examples where you won't be doing any type of integration. You won't need calculus to solve these. There'll be simple algebraic explanations or graphical explanations. But we need to look at a PV diagram and talk about the area under the curve of a PV diagram. And we'll look at very explicit examples where the pressure doesn't change, the volume doesn't change, the temperature doesn't change, or the amount of heat is 0. We'll look at that in just a moment. Here are two very simple to understand processes. The first one is called an isobaric process. Now, remember, baric, like a barometer, it measures pressure. So this is the constant pressure. Iso means constant. Baric is like, again, barometric pressure. So this is a constant pressure process. So if we look at our pressure versus volume diagram, our PV diagram, when we have some state here, I dubbed it I for the initial state, and we go to some final state. So see how the volume changes, right? The volume goes from some initial volume to some final volume. So the volume of this system increases. However, the pressure remains constant, right? Isobaric, constant pressure. The pressure doesn't change during this process. So while this thing is expanding, the pressure on the inside of the wall isn't dropping. It's staying at a constant pressure. Well, the work done is the area under the curve or line on a PV diagram. Well, this is just a square, right? Area under this line is this rectangle. So this rectangle, one side, the height, assuming that this is pressure of 0 down here and this is a volume of 0. This side of the triangle is P. Sorry, of the square rectangle is P. This side of the rectangle isn't V sub F because it doesn't start at 0 volume. It's this length, which is the difference, V sub F minus V sub I, which is delta V. So the work done in an isobaric process is the pressure, which is constant throughout this process, times the change in volume. So that gives the work for an isobaric process. Another simple to understand process is isochoric. This just means constant volume. So now the pressure is going to change, but the volume will remain the same. So here's the pressure from some initial pressure, P sub I, at this point, P sub I, to some final pressure, P sub F. The volume V remains constant. So we have a vertical line going straight downward. Now remember, the work done is the area under the line. But the problem is this line has no area under it. It's a straight vertical line. There's no area under that curve, under that line. Since there's no area under the line, the work is equal to 0. You can kind of see that here, right? The work is pressure times the change in volume. If the change in volume is 0, no work is being done, which is what you get for an isochoric process, no change in volume. Now this is just for a simple process where you go from some initial to some final state. So on this PV diagram, whenever you go from change your pressure or change your volume, you're changing the state of the gas. What if you have a cyclical process? A cyclical process is just a series of state changes that bring you back around to your original state. So for example, I have this example down here. We start at state number 1. There's an isobaric process that takes us to state number 2. An isochoric process that takes us to state number 3. Another isobaric process, but now backwards, that takes us to state number 4. And another isochoric process that takes us back to state number 1. So I've created this rectangle here. 2 isobaric processes, the top and the bottom. 2 isochoric processes, the left and the right. We start at point 1 and we come back to point 1. So this is called a cyclical process. In this cyclical process, the work done is the area inside this loop. Now, we don't really have a loop here, like a circular loop. It's a square. So it's the area inside that square. Here you can see that the work goes all the way down to pressure of 0. Whenever the volume increases, if this is a positive increase, the work done is positive. If it's a negative volume change, if the volume is shrinking, delta V will be negative and the work done will be negative. So what happens is the process from 1 to 2 is the same as from I to F here. You look at the entire rectangle under 1 and 2 for the positive work done by that process. But when you look from 3 to 4, from state 3 to 4, you get a negative volume change. The volume is shrinking as it goes to the left. Since the volume is shrinking, you get a negative work done under that curve, so you have to subtract it off. So the area for a cyclical process then becomes the area inside that circle. Now, this is a very simplistic process, not very realistic. There are a couple of other systems, other processes that are a bit more realistic in terms of heat engine. Those are isothermal processes and adiabatic processes. We'll talk about those in a moment. Two other common processes in a PV diagram. You have isothermal processes. We talked about those earlier. These are processes with constant temperature. So if you have constant temperature, then PV, which is equal to nRT, if the number of moles doesn't change because it's a closed container, R is a constant. If the temperature doesn't change because it's a constant temperature process, PV is equal to a constant. So P isn't constant like it is an isobaric process. V is not constant like it is an isochoric process, but P times V is constant. So if you increase P, V must decrease, and so on. This is called an isothermal process, and basically what it means is heat goes into work. The change in energy of the system is 0. And this last process is called an adiabatic process. Adiabatic process is a process with no heat transfer, so Q is equal to 0. No heat is coming in or leaving the system. So a PV diagram for a more realistic engine called a Carnot engine, we'll talk about those in a bit, you have, rather than a square, you have an isothermal process from state 1 to state 2. That is an isotherm, it's called, a line of constant temperature. Then you have an adiabatic process from 2 to 3, isothermic process, so the arrows are going in this direction, isothermic process from 3 to 4, or isothermal process from 3 to 4, and then from 4 to back to state 1, so this is cyclical, you have an adiabatic process. So the work is the area inside this strange looking four-sided object. So this tells you, if you had the calculus to be able to do these integrals, you could figure out what the work is for this type of a process. Again, this is a bit beyond the scope of the class to figure out the work done, but you do and should know what these two types of processes are.